Hello class, welcome back. This is lecture number 13, chapter 12, called The Dynamic Planet. Will be the final set of lecture notes prior to exam number 2. So it'll cover lectures 9 through 13. Remember, lecture 9 is 3 parts. So this chapter in the textbook is really extensive, and this course is not a geology course. So I'm not going to have you read this particular chapter and do a reading quiz on it. However, if any of these subjects or topics are a little confusing, you can always reference the book. I'm all for reading this chapter in the textbook. I just felt like trying to give you guys a little bit of a break in terms of reading. And since this chapter it's related and it's important because of what we're going to talk about later, it's not super involved. And if you take a geology course down the line, you'll cover much of this stuff going forward. So the idea today is to talk about some of those geologic features that are ultimately going to lead us to the oceans and to soils that we'll talk about in the next several lectures. So as it says here, this is kind of the outline. So we're going to talk about the pace of change really quickly, very simple kind of topic. We'll look at Earth's internal structure. I'll just give you some basics about the internal dynamics of Earth. Talk about the rock cycle a little bit, something you've probably covered in high school or another earth science or environmental science course. And then wrap it up talking a little bit about plate tectonics and the movement of Earth's overall crustal features. So that's what we're going to be talking about today. So the first definition is really simple. It's called uniformitarianism, so it's a huge word. But in reality, all it means is the word uniform. So the stuff we're talking about today, whether it is a volcano or an earthquake or plate movement, we're going to assume that that's what's been happening in Earth's past, and it will continue to happen in the future. Right? So all of these features are uniform. So they've been happening, they are happening, and they will continue to happen throughout geologic time is the idea. So Earth's structure itself is something important, especially the upper levels, which are what we're going to be focusing on mostly in this course. But I thought I'd go through just a brief overview of a cross-section through the Earth. So if we were to take the Earth, which is down here, and take basically like a slice of pie from where we live up here near the ground level, all the way down to the Earth's center, and we pull it out, it's going to be this triangular looking wedge like this. In fact, I think the textbook blows it up. Yeah, so here's our blown up picture from here's the center of the Earth all the way up to where we are right now. So when you break these down into pieces, what I want you to be able to identify is what the center of Earth is called. So the very center of Earth, this kind of grayish purpley area, this is Earth's inner core. The inner core is the center, and it is the area that has the highest temperature, pressure, and density. So as we're heading downward through the Earth, temperature, pressure, and density are all increasing the deeper down you go. So in the inner core itself, this is where all of those variables are the highest. The pressure is the highest, temperature is the highest, and the density is the highest in these regions. And it shows you the density here, 13.5 grams per every cubic centimeter that there is. When we head above this, we move into the outer core, which is the next layer. And then, depending on which textbook you look at, ours breaks into the lower and the upper mantle. But for simplicity's sake, we're just going to call all of this section here, from this point all the way up here, just the mantle. Then we have this layer called the asthenosphere. Then we have this layer called the crust. So from top to bottom, we have the crust, and then beneath the crust is the asthenosphere. Beneath that, we have the mantle. Beneath that, we have the outer core, and then the inner core. So the idea is that as we drill down through the Earth, so if you were to dig down, straight down, you move through the mantle, and the mantle is a solid layer of iron, magnesium, all sorts of metals and rocks. This is a solid part of Earth. But as you're getting deeper and deeper, the temperature is increasing. So eventually those rocks and those metals begin to melt. And they melt along this line here, which is called the Gutenberg discontinuity, just named after the scientist that figured this out. And right along, that's why this thing looks so jagged, because some rocks are going to melt way up here. Some are going to have a higher melting point. They're going to melt all the way down here. So you get this very jagged layer. So then as you get deeper than that, this becomes the liquid layer. So the outer core of Earth, this kind of greenish zone, is liquid or molten, mostly iron. So it's a liquid layer within the Earth, and it's very, very hot. So this is liquid, molten, or metallic iron in the center. But then as we get even deeper and we move back into the inner core that we first talked about, this grayish purpley area, the inner core, as it says there, is solid. If you think about it, the temperature keeps getting higher and higher and higher, and it melts and turns into this liquid that's here in the outer core. But eventually, as the temperature gets higher and higher, it eventually turns back into the solid state, which doesn't seem to make sense from a temperature perspective. But if you think about it, temperature was not the only thing that was increasing. As we're getting deeper and deeper into the Earth, the pressure is also increasing. And the pressure is so high there that the pressure forces those metals back into the solid state, right? So that's the first thing that I want you to know. The inner core is solid due to the high pressure. The outer core is a liquid layer due to the high temperature. And then the mantle is another solid layer. The crust is a solid layer as well. It's what we live on. So when you leave, if I were to leave this building and walk outside, I'd be walking onto Earth's crust. And then we get this thin layer between the crust and the mantle, and it's called the asthenosphere. And this is a unique layer, and I'll talk about it in a little bit, but it's partially liquid. There are pockets of liquid. It's about 10% or so liquid, and it's due to radioactive decay. So there's some materials underground that decay radioactively, which gives off heat, and then it's going to melt the neighboring rock. So you're going to get these little pockets of liquid in that layer. And that layer, more informally, is going to be called the plastic layer, because you're going to see that rock layers are very rigid and tough. They don't really move much. But because that layer has some liquid intermixed in it, that layer is going to have some give to it. So it's going to be somewhat flexible. So they call that the plastic layer. Okay, so that's just a real quick overview of some of the layers that are beneath us. And we're honestly going to spend almost the entire rest of this class and all the rest of the time we look at solid Earth stuff talking about the crust, because that's where we are up here in the upper levels. Right, so a couple things about each layer before we jump into that. So the Earth's core, as I said, it's 1/3 of the entire mass of Earth, but is only 1/6 the volume. So if you think about that, what does that mean? It is 1/3 of the entire Earth's mass. So it's a huge chunk of Earth's entire mass, but it's not that much of the volume. It's only 1/6 of the volume. So if you think about logically what that is, that's talking about density. So while this area might not be that big, it's very, very dense. So it has a very, very high mass to it. So we said it's broken into two regions, the inner and the outer core. The inner core is solid due to the high pressure, and the outer core is liquid. The temperatures range between 5 and 12,000 degrees is what we said. So the structure looks like this again. And just as reference, we've only ever drilled down about 12 kilometers downward, which is about 7 miles. So the deepest drill down is right where I'm pointing, maybe right into there. That's all the farther down we've gone. So how do we know what all the rest of this looks like? Well, we use indirect evidence, so waves basically. So as it says, it's based on how seismic waves travel through the Earth. So basically, if you think about it, it's just like when we're talking, right? When you can hear me, you're hearing the vibration. So when I speak, my vocal cords vibrate, and they send out waves of pressure through the air, which our ears pick up. If I'm talking to somebody, and then we both go underwater, and we talk to each other underwater, you can still hear the person, but sound is very different when you're under the water because the sound wave travels through the liquid very differently. So this is what they're able to do. They're able to detect how the waves travel through these layers of Earth. Sometimes, if it's going quickly or differently, it might indicate liquid, it might indicate solid, that sort of thing. So we can pretty much theorize what the inner layers of Earth look like. But don't get me wrong, we have not visited these layers. So if you've seen some of those Hollywood movies like the movie The Core, where they go down in this little shuttle thing and they explore the middle of the Earth, that's Hollywood. That doesn't happen. So keep that in mind. We've only gone down about 6 or 7 miles. And that's only with a drill. That's not with people. So just keep that in mind. So as it says here, the inner core is made mostly of iron. It's solid because of the enormous pressures. As it says there, enormous pressure keeps this inner core solid. The outer core is liquid. So again, it's because temperatures are approaching really, really high values, 6, 7, 8,000 degrees, and it melts the iron in this layer. And that's what basically creates this molten section. Now, why are these two layers super important for us? You might say, well, they're deep beneath the Earth. We're never going to visit them. Why are they important? Well, they're important because they generate Earth's magnetic field. So the idea is, as Earth is rotating, the liquid inside Earth is also spinning. And anytime you get current or highly charged particles spinning in a circle like that, they emit a large magnetic field. And this is a huge circulation. So it creates a ginormous magnetic field that surrounds the planet, which is very important for us. That magnetic field, it's what controls a compass and tells it to point north. But more importantly, the sun gives off all sorts of really nasty types of particles and radiation that approaches the Earth. And when it hits our magnetic field, it is deflected away from the Earth. And it really protects us, as it says here, protects us from solar wind, which is those really nasty, highly charged particles from the sun. So without the magnetic field, we could not survive on Earth's surface. We would be bombarded by these solar particles. And the magnetic field on Earth comes from these layers within the center. As it says, at least 90% of the magnetic field comes from the liquid outer core and the fact that it's rotating around. Now, there are some new theories that suggest that it's a difference in rotation between the inner and the outer core and the Earth itself, and that creates exactly the shape and whatnot. So again, this is theory, so no one knows 100% what the answer is. So there are different competing theories out there. But it's pretty well accepted that the fact that the outer core is liquid and it's rotating, that's what's going to generate that protective magnetic field that surrounds the planet and protects us again from those really nasty types of radiation that are coming in from outer space. Then we move upward, so we leave the core, and right where the core has melted, and then you go into the mantle again, that kind of disjointed layer where it's melting is called the Gutenberg discontinuity layer. And this is that uneven kind of bumpy zone named after the scientist that discovered it. So that's the transition zone between the outer core and then the mantle higher up. The mantle we're not really talking much about. It's a solid feature. It's made of a variety of metals, iron, magnesium, silicon. It's about 80% of Earth's volume. So most of Earth is the mantle, right? But for our purposes, it doesn't create a magnetic field. It's not what we live on. It's not what we interact with. It doesn't create the earthquakes and volcanoes that we have. But it's important because it is the majority of Earth, 80% of the volume. But for our class, we're not going to talk too much about the mantle. Just know that that's what that layer is called. So then we move to the upper part of the Earth. So we live on the crust, which we're going to spend most of the time on. But the thin layer that's right beneath us is called the asthenosphere. And as I already mentioned, this is known as the plastic layer because it has pockets, as it says here, of about 10% molten material. So it's about 10% liquid. And it's there because of that naturally occurring radioactive decay, which basically just heats and melts some of that neighboring rock. And again, this is going to be flexible, so there's going to be some give to it. So as it says here, this is the zone of plate tectonics, earthquakes, volcanoes, and we're going to talk about this later when we talk about upward moving liquid and its formation of some of these features. And we'll talk about that towards the end of the lecture. So we'll get back to this. So to put all these things into perspective, I really like this next graphic that the textbook has. It shows each of the layers that we just talked about. So there's the inner core, outer core, all of this is the mantle. And then we have the asthenosphere, and then the lithosphere, right? So, or the crust. If you were to lay those layers down across the United States, that's approximately how deep it would be. So if you wanted to travel to the center of the Earth, it would be like driving from San Francisco all the way over to the East Coast over on the Atlantic Ocean. So the width of the United States is approximately how deep the Earth is, if that makes sense. And it shows you kind of perspective how long it would be in each of those layers if you were traveling across them. So very, very, very deep in terms of all of the layers, really. And then the crust is, of course, the thinnest of all of those layers that are listed there, right? So that's what we're going to spend the majority of the rest of our time talking about, is the differences in the crust and then what the crust ultimately does for us. So there's two types of crust that we see. There's what we call continental and what we call oceanic crust. And they are exactly what you would expect. It's basically the land that makes up the continent is continental crust, and it's made mostly of granite. And most of you know what granite is. You've probably seen like granite countertops and things like that. You can see the metals and crystals that make it up. But that's going to be the majority of the rock type in continental types of crust. Oceanic crust, so the floor of the ocean, the rocks and material that makes up the floor of the ocean, is made mostly of what's called basalt. And basalt, you probably have not heard of this before, but if you have, it's a denser type of rock. So it's a heavier, much denser type of rock. So what you're going to see is that the ocean crust is going to be thinner than the continent, but it's going to have a higher density to it, is the idea, right? So where this is going to come into play is that third bullet point, which asks you about buoyancy. So buoyancy, remember, is something's ability to float, right? So if you put water and oil together, the oil will float on top of the water because it's less dense, right? So if I tell you that the continental crust is less dense than the ocean, when the two of them collide, the ocean is going to go down and sink, and the continent's going to float on top of it. And that's why this is important to understand their density. So again, the continental crust is less dense. Oceanic crust has the higher density. And when the two meet, the continent is going to float and the ocean is going to sink. And we're going to talk about the implications that this has down the line. Right? So the idea looks like this. So if we're looking at this top section, here's our continental crust. So it's thicker. This green layer is thicker than the ocean. The ocean is the blue layer, but it's less dense. So when the two meet, so imagine this blue is moving to the right, the green is moving to the left. The two meet right here. Notice the ocean sinks beneath the continent, and the continent goes over top of the oceanic crust. This, by the way, and we're going to define this later, is known as subduction. So when you have heavy oceanic crust meeting less dense continental, one is going to float, the other is going to sink, and you create this kind of a picture where it just slides like that over top, which is what this picture is trying to illustrate. So a thicker continental crust, but less dense, and a thinner oceanic crust, and it's more dense. And that's what we see as the difference between the two types of crust. Now, what you're mostly probably familiar with from an earth science class you maybe took in high school or something is that the fact that the crust moves around. So the plates are moving. You've probably heard of Pangaea before, the big supercontinent, and it all split apart, that sort of thing. And we're going to talk about that in a little bit. But I wanted to start off with saying that the crust doesn't just move horizontally from side to side. The crust can move vertically, which is an upward and downward motion, which we call isostatic adjustment. And isostatic adjustment is just that. It is vertical movements of Earth's crust. So imagine I take a piece of paper and I say, this is the Earth's crust like this. Right? And then a big glacier forms, a big chunk of ice forms on top of this. What's that going to do? Well, it's going to crush the continent. It's going to make it go down like that. But then as the ice melts, what does the crust do? The crust slowly pops back up to its original position. So that's what isostatic adjustment is. It is when you put a lot of weight on the crust and it forces the crust down. And then when that weight is removed, the crust then pops back up. So that's the idea. So this is what the textbook shows. The textbook says, all right, let's say a mountain develops, volcano erupts and sends all this rock up onto the surface. And then we have a big mountainside here. All of that weight is going to push down on the crust. So the crust buckles downward. So there's our isostatic adjustment. It's adjusting downward. But then through rivers and erosion that we talked about in lecture 12, the rivers are going to erode away these mountains and carry it downstream and dump it over here in the ocean. As it's removing the weight is being reduced. So what does the crust do? The crust pops back up. But then if you think about it, this weight is being moved from here, and now the weight is being put right there. So as you add more and more weight, this becomes heavier, and look what happens to the crust here. The crust starts to sink in this region. So while the weight is being removed over here and the crust pops back up, the weight on the other side is being increased, and then it sinks back down. So this is how the crust can vary its upward and downward motion. And glaciers do this as well. So when a glacier forms, all that mile or two of ice crushes the crust down, and then when the ice slowly melts off, the crust comes back up. So again, those are examples of what we call isostatic adjustment. All right, so that's a little bit about the solid Earth, the deep Earth features, and we'll talk a little bit more about them towards the end of this. But for right now, I wanted to cover something very simple, at least initially simple, and then I'll add a little complexity to it, and that's the rock cycle. Now again, I'm sure all of you that are watching this have seen the rock cycle in one of your middle school or high school classes before, so humor me. There's three types of rock. There's igneous rock, there's sedimentary rock, and there's metamorphic rock. Igneous rocks are rocks that are brand new. So they come from liquid. So if you visit Hawaii and you see liquid rock like this, where it's superheated and it's melted, when it cools off and solidifies and turns into rock, which is right here, that is igneous rock. So igneous rock comes from liquid. Now there are two types of igneous rocks. There's what we call extrusive igneous and what we call intrusive igneous. Igneous rocks that are extrusive means that the liquid that was under here underground made its way all the way up, perhaps out of a volcano, spills out onto the ground, and is all over the ground, and then it cools and solidifies into rock. So extrusive means when it comes out of the ground and then cools onto the surface. That's an extrusive type of igneous rock. Now the other type is intrusive. So this is when the liquid works its way up to a certain point, but doesn't make it out onto the surface, so it just solidifies. So it becomes solid under the ground, and we call this an intrusive type of igneous. With extrusive, that's the magma and the lava that makes it to the ground level and then cools and solidifies. And then intrusive, and then this is the igneous that is formed underground when it solidifies. So those are the two types of igneous rocks that I want you to know. All right, so igneous, new rocks. The second type of rock is sedimentary rock. And sedimentary rocks are formed, as you can imagine, from sediment. So the idea is here's our mountainsides. As they erode away, there's our rivers. They're carrying sediment, and they dump it here into the ocean. And layer after layer after layer of sediment builds up over time. And what happens is, imagine you get some sediment, then you get some more sediment, and then more and more and more. And the weight of all that sediment starts to push down, and it solidifies the sediment that was down at the very bottom. That process is known as lithification. So as it says, sediments are transported that accumulate and then slowly cement together because of the weight of all the other sediments start smushing it, and it basically solidifies into rock, and we call that process lithification. And that's what sedimentary rock looks like. So we have igneous, which are new rocks, sedimentary rocks, which are formed from sediment solidifying, and then we have metamorphic rocks. And the word metamorphosis means to change. Right? So these are rocks that change. So whether it's an igneous rock, a sedimentary, or another type of metamorphic rock, if it's either heated or given a lot of pressure to it, it's going to change its internal structure. So this is a rock that doesn't melt, but perhaps you add enough heat to it so it becomes kind of flexible, so then you can reshape it, is the idea. So the example is this. So for metamorphic rocks, there's two types. There's what we call contact, which is, it says, when rocks are drastically heated, but they're not melted. That's the key, because if they're melted, then they turn into igneous. They're not melted. They become kind of flexible, pliable, and then they reform, or they cool off, and they've slightly changed their structure, and then they're called a metamorphic rock. The other one is from compression. So if you have a rock, but then it's under tremendous amounts of pressure from the plates moving or some other force, it can crush the rock down and reshape what the rock actually looks like under that really high pressure, and that is known as compression. Right? So those are some real basic pieces of information about the rock cycle. And why this is important is when we get into the ocean lectures, and especially when we get into the soil lectures, we're going to talk about weathering and erosion. And you'll see that certain rocks are going to break down more efficiently and create soils than others. So we'll get back into talking about some of these topics in a little bit down the line. But for the rest of today's lecture, I really want to focus on some of the plate tectonics, some of the plate movements, some of the things that the plates form and what they do for us up here at the ground level. Since that's what we live on, is we live on the plates, we live on the Earth's crust. So that's the idea. So the idea of movement, the formation of the different continental areas and mountains is a concept called seafloor spreading. And this concept is fairly new. It was first proposed, as it says there, in the early 1960s. So that's been, what, about 60 years ago, roughly. And it's basically the mechanism, as it says, that builds mountain chains, that drives continental movement, and it's going to cause all the major things, the major geologic things at the surface that we see to occur. So the idea is, it's easier just to show you a picture. So what this graphic is showing is this is South America over here to the west. Here's Africa to the east. And here's the Atlantic Ocean in between. Now, all the water has been drained out of the Atlantic. So you're just looking at just the rock features, right? So the idea is in the middle of the Atlantic Ocean, there's this giant crevice, this big crack in the ocean floor, which is called the Mid-Atlantic Ridge. It's where the ocean plate has a big break in the very center of it. And what happens at this break point is liquid from beneath oozes upward, and some of it spills out to the right, and some of it spills out to the left. And more and more and more liquid just keeps spilling out onto the seafloor. And that's what creates all of these ridges. You're just creating all these new rocks. But as more and more material comes out here, this part of the rock starts to move away from it, just because to make room, as does this side. So basically, this is what is called seafloor spreading. So the seafloor is physically separating due to this material coming up out of the ground, forcing the separation. Right? And that's what the process of seafloor spreading is. So as it says here, it's the upwelling of magma, or that liquid rock, from the hot areas in the upper mantle, and then it spills out onto the seafloor, and it forces these zones apart, and it spreads out laterally. But if you think about what that does then, is then this whole section of Earth from that break point all the way over to South America. All of that starts moving to the west. Then we have all of this eastern side that's connected to Africa, and all of that moves off to the east then. So the continents start moving apart. Well, what does that cause? Well, that causes South America then to run into the Pacific Ocean. And these plates then run into each other. And like what we said, the ocean's plate is heavier and denser. So when it runs into this, it's going to sink or subduct. And it sinks beneath the continent. And as it's sinking there, it melts, liquefies, and all that material then starts bubbling up to the top here. And you create this mountain range, which are the Andes Mountains. Right? So you can see all of this is driven by this seafloor spreading concept. It starts moving the continents, and then they run into other things, and they create mountains and volcanoes, and it's just this spiraling effect from this is the idea. All right? So, okay, so basically, sorry about that, someone came to my door. Basically how scientists figure this out is to figure out the Mid-Atlantic Ridge feature here is they go to the center part of the ocean like this. And they can sail their ships and they launch their little submarines and basically they go down there and they can see where this material is bubbling up out of the ground. And what they're able to do is run chemical tests. So this red line represents right here in this one particular spot of the ridge area where that material is bubbling up out of the ground. And then these are chemical matches on either side of where that material is coming out. So what this means is the material comes up out of the ground, some of it goes to the right, some of it goes to the left. And then it moves away, and then it moves away, and it moves away. So then what you see is the stuff that's over here chemically is identical to what's over here. And then this blue is chemically identical to this, and this purple is that. So this implies then that this material is coming out of the ground here, splitting, and then spreading out like that. So this is strong evidence to suggest that this is happening. And we can physically now measure with our satellites and technology the actual movement of all of the continents and whatnot. So it's very little theory now. We pretty much know that this is what's happening, and it moves the continents around. So as I mentioned, subduction is when the ocean and the continent collide together. When they meet, ocean sinks, continent floats, and what happens, again, just to summarize, is as this sinks, it's getting deeper and deeper. It's getting hotter and hotter, so it melts. And this liquefied rock then slowly rises to the surface like this, and this creates these big volcanic mountain ranges that we see, the Andes Mountains in South America. So that's what subduction is. It's when the denser ocean floor dives beneath the lighter continent, and it creates those mountain ranges that we see. So now this seafloor spreading is forcing big pieces of Earth to move around, and those pieces of Earth, of the crust that are moving as one unit, are called plates. And so there are really 14 major plates along Earth. Half of them are really big plates, major plates, and the other half, the other 7, are minor plates, some smaller plates. And again, plates are just pieces of the Earth's crust that are moving in the same direction. So I can just show you the map here. So this shows you the map of the world and divided in its plates. So what we've been looking at is the South American plate, so I'm kind of outlining it right here. This section right there labeled South American plate. Here's the Atlantic Ocean. There's the ridge that separates the two plates. And then here's the African plate. So here's Africa over here. And you saw from those images before that the plates are separating right here along the central boundary. The plates are moving apart, right? So there's 3 types of plate boundaries, knowing this. There's what we call a divergent plate boundary, a convergent plate boundary, and a transform plate boundary. Divergent plates are plates that are separating apart. So that is an example, this ridge section here in the Atlantic Ocean, where the South American plate is moving away from the African plate. You can see the North American plate is moving away from the Eurasian plate. They're moving away from each other. Those are divergent plate boundaries. There are some plate boundaries, though, that are moving towards each other. So when we saw the subduction zone here, notice here's South America. Notice it's moving into this smaller Pacific plate. These 2 plates are moving towards one another. So those are convergent plates. And then sometimes you'll have situations where the plates are kind of moving side by side. So they're moving along one another. And those are called transform plate boundaries. So again, divergent means they're moving apart. Convergent, that means they're moving towards. And then transform means that they're sliding kind of parallel side by side like this. And the transform ones aren't as widespread on these big global pictures, but they're really localized. So like the San Andreas fault line in the western part of the United States, that's a transform plate boundary. All right. So what scientists tried to do then is say, okay, if this is the current picture of Earth, how did the Earth look, 10 million, 50, 80 million years ago? Well, one way of thinking about it, and a very elementary way of doing it, is to say, all right, well, Africa is moving to the east, South America is moving to the west, so just back them up over time. So just reverse them. But the problem with that is that assumes that the speed and the direction don't ever change, and we're pretty sure that it does, so you can't really do that. Another really elementary way of doing it is to say, all right, well, the eastern part of South America, just look at it, and then look at the western part of Africa, right? It doesn't take a very large leap to say that it looks like South America fits inside this gap in Africa right there. You could just move this section and just stick it right there, and they fit together. Now, that's even less scientific than the previous way, so we don't do that either. What scientists do is they go along the eastern part of South America, and they would drill down through here as deep as they can go and take all this rock samples, the core samples, fossil records, and they would do all this chemical testing all the way up. And then they do the same thing on the western side of Africa. And if they were once together, when you get deep enough, the things should match up identically. And that's what they do all around the world to try to match up where the plates used to be. As they go way down, they take all the records and then they match them up chemically. And where they match then implies where they used to be. So that's what's done. So over time, remember, again, this is theory. There's a lot of work that goes into this. But this shows you 400 or 500 million years ago. But here's the most famous one that you've probably seen before in a middle school textbook. And that's Pangaea. This is the supercontinent where all the continents were joined together as one. So one continent and one ocean. Right, that was it. And then over time, the plate boundaries formed. And we see them here, these blue lines, and the continents slowly started to separate. So you see South America and Africa are still connected. This is 65 million years ago. You see that the Atlantic Ocean is very shallow and narrow. The Pacific Ocean is the dominant ocean. But look at India. India was its own island, right? India is moving northward, and India slams into Asia. And what do you create? You create the Himalayan mountain range, is what you get. And then you see Australia and Antarctica were one continent. You can go down into Antarctica and drill way down, and you find all the fossil records of all the plants and animals that used to live on Antarctica. And they match with what used to live on the western side of Australia. So it's very, very likely that those two continents were once one continent before Antarctica moved towards the southern polar region of Earth. And then this is what the Earth looks like today, right? So we see the continents, and these are our current plate boundaries. So what we can imply from this then is with each passing day, North America, so where we are, we're getting a little bit farther away from Africa and Europe every day, but we're getting a little bit closer to Asia on the other side, right? So the Pacific Ocean is slowly getting smaller, and the Atlantic Ocean is slowly getting bigger over the years. And then these other graphics are just showing you convergent, divergent, and transform plate boundaries, but we've already mentioned those, so that should be pretty straightforward. All right, so the very last topic for today is to talk about what are called hotspots. And hotspots are these areas that I already mentioned in the asthenosphere underneath us that is 10% molten areas. They're liquid under the ground level. And basically what they do is they become active and they send a bunch of liquid, this magma, this molten rock up to the ground, and they form a volcano. And then that volcano is stuck to the crust, and then the crust moves away. And then the hotspot sends more material up, creates another mountain, which is connected to the crust, and then the crust carries it away. So basically, you just keep creating mountains, which then the crust just carries away, and that's what Hawaii is, as you're going to see in a slide or two. Well, let me just show you the Hawaii picture first. So this is what Hawaii is. There's a hot spot right here, so liquid just keeps bubbling up. So if you ever visit Hawaii, you can go and you can just see the magma coming right up out of the ground. But Hawaii is connected to the plate, and the plate, as you can see here, is moving towards the northwest. So the material comes up here. So at one point, these islands that were here were over where Hawaii is right now. They bubbled up out of the ocean, and then they floated, or they're connected to the crust, so they're forced to go this way. So this is the huge Hawaiian island chain here. Right? All these little islands that are out here, Midway, you probably heard that from history class. These islands used to be over here where Hawaii is. And then over time, they bubble up out of the ground, and then they slide along the crust. And you can see, it's called the Hawaiian Ridge for a reason. You can see it on the topographic map when there's no water here. You can clearly see the islands going from where they currently are all the way up to where the Aleutian Islands are in Alaska. Now, these hotspots are not just here in Hawaii. This is a map showing you all the plate boundaries on Earth and where we see our major geologic features. So the red triangles represent volcanoes. The orange circles represent hotspots. Right? So if you just look at those two things, notice the western side of North America, all the volcanoes and hotspots. They go down all through South America. Right? If I were to draw a circle, that would include all of these and through Alaska. Right? It's basically, they're all of them right along the plate boundaries. So look at the eastern United States. We don't have any hot spots. We don't have any volcanoes here. They're all isolated out to the west. Washington State, Oregon, southward through Mexico City, and then down through the Andes Mountains. And then if you look over to the Pacific Ocean, they go from Alaska down through Japan, through the Philippines, north of Australia. They surround this area, all along the plate boundaries. Right? So again, you should see from this picture that almost all the volcanoes and hotspots that we see are right along those plate boundaries. Right? Because again, you get all this movement and converging plates, and they're going to force volcanoes or subduction or something to happen. Now they're not always like that. Like Hawaii has its isolated ones, there's some isolated ones in Africa. So they can form outside of the plate boundaries. But the majority of our major earthquakes, the majority of our major volcanic eruptions are along those primary plate boundaries that you see on this graphic. So it's important. And in geology, this section, so all of Western, South, and North America over here, and then all of Eastern Asia and the Philippines in this area, when you draw a circle around Earth, imagine this would be one side of the circle, and this would be the other side of the circle. In geology, that's known as the ring of fire. So this is the ring around the Pacific Ocean of all the continental areas. These are all plate boundaries, and that's where the most active areas of volcanoes and earthquakes are on Earth. Now, there are some others certainly across parts of Turkey and the Middle East and things like that, parts of Africa, but the majority of the earthquakes and volcanoes are here or in this region here. And again, that's known as the ring of fire. Right? So that's a little bit about where these geologic things are located. All right, so that's going to wrap up lecture number 13, and this ends the material now for exam number 2. So again, I'll be posting the similar review sheet to what I did for exam 1, as well as having one of those conference review sessions a day or two prior to exam number 2. All right, so stay tuned for those. Thanks for watching, and I will see you after exam number 2, and we'll jump into the last set of lecture notes for the course, and we'll start talking about the oceans. All right, well, good luck on exam number 2, and I'll see you all soon.